So what is a circle? How do we define circle in general sense? We have seen many objects in real life which define a circle. Say for example, I have a shape of this stapler, of this sellotape which looks in circular shape. So this kind of a shape which we see in real life is a circle. This board is not a circle because it is not circular. So by seeing the shape, we can identify whether it is a circle or not a circle. In this case, the rim is a circle, but the face, the width face is not a circle. Similarly, I have a disc which has many different circles as can be identified. One of the outer circle is this because it is circular in shape. The other circle is the rim out here, and there's one more inner circle. So these are the different sizes of the circles which are identified in the disc. The bigger circle, the next bigger circle, and the smaller circle. So circles can be of different shape, but anything which represents the shape of being round is called a circle. There are many examples in real life which can be taken along with the two example models which you have considered. Like you can take the clock, the wall clock usually comes out the circle. Introduction. Of the circle. Imagine I have a wall clock where my second's hand moves in this direction. It goes on and etc. So this second's hand which moves in this clockwise direction in the wall clock tries to make, retain back here, tries to make a circular motion. So the motion made by the tip of the second's hand in the wall clock is called circular motion. So a circle is something which is formed when any object rotates round its fixed point. So any object which rotates on fixed point tries to make the outer margin which looks like a circle. Is how we define in the general sense of understanding a circle. The currency coin, a 1 rupee coin, a 5 rupees coin, a 10 rupee coin, etc. are all circular in shape. So they are all circular in shapes. Is how we understand a circle in real life model. This is a circle, this is a circle, this is a circle, and this is a circle. For example, I take a photo frame which defines a lady out here. This is not a circle. because you take the fixed point and move the side, it does not form a circular shape. Any fixed point and then move, it does not form a fixed shape. So any object when taken with a fixed point and then rotated around its rim, the kind of a shape we get is called a circular shape. So a circle is something which has fixed point and moves at constant distance throughout in all directions, just like the seconds hand of a wall clock. To take an example of circle, 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 not a circle, is how we understand the concept of a circle. Circle in mathematics. Now that we have discussed about what a circle is, like how does a circle look like, what is its shape, now that we can recognize a shape to be a circle or not a circle, now comes the question, how do we draw a perfect circle? When I draw by free hand, it is not that easy that I get a full circle. For example, when I just draw, I may move out and I get a kind of a circle which is not perfect. So I don't get a perfect circle. So my question here is it perfect? No, it isn't. So how to draw a perfect circle on a sheet, on a rough sheet, is the concept which you're going to see in this session. Construction of a circle is today's session. Construction of a perfect circle. So let's see a perfect circle in its construction. When I take a fixed point, let me take a compass from the geometrical instruments. We all are aware of a compass. So we took the pencil and just put the point of the compass out here and move with certain radius or with certain distance and try to move the pencil out here. So I get a kind of a shape which looks like this. So I get a shape which looks like this with the fixed point of the compass. So the kind of shape I get when I take the fixed compass and move the pencil round throughout the page is what a perfect circle is. A perfect circle is obtained by using the compass. So here the compass gives me a circle derived from a compass. A circle derived from a compass. And this is no doubt a perfect circle. This is perfect. Circle is how we conclude. So any circle which is derived from a compass gives me a perfect circle. So for a construction of a circle which needs to be perfect, we use the compass and then draw it around the page and we get a circle of this type. This is not a perfect circle because it's drawn by freehand, but this would be a perfect circle if you can join through the compass. It's how we understand constructing a circle with and without compass. Now that we have seen the circle and its shape and the construction methods of constructing a perfect circle, now comes in understanding the mathematical definition of a circle. Mathematically, we need to understand what a circle is. So this session is about investigating the mathematical definition of a circle. So let's see how we define a circle in mathematics. Mathematical definition. Let's come back with the construction of a circle using compass. As we have discussed in the previous session, that a perfect circle is obtained when we derive through a compass. So we have taken the compass fixed at here, and when I take the rotating, I get a circle in this manner with a fixed point out here. Is how we understood a circle. So how do we define mathematically this fixed point which derives a perfect circle? Well, when I move the compass with the fixed point fixed out here, and at half the way I move it here, do we get a perfect circle? So my question here is, can we get a perfect circle if this fixed point is moved in midway when we derive the circle with the compass? No, we cannot. One can investigate using a compass to move the compass out there, the pointer out there, and then try to complete the circle. In the halfway, we cannot get a circle. A perfect circle is obtained only when the pointer of the compass is fixed exactly at one particular point, no moving aside. So this makes us clearly understand that for deriving a perfect circle, this must be a fixed point. The pointer must be at a fixed point, is how we understand the first investigation of a circle derived from the pointer, is how we understand through this. Now, as we see clearly that as the pointer with the pencil which moves out here derives a perfect circle, I clearly see that whenever I derive a perfect circle through the compass and measure the distance between this fixed point and this corner off with the ruler, I get same distance. That is, the distance I measure here and the distance I measure here, or the distance I measure the other side, throughout the circle, I see that all the distances I measure will be at equal distances. Taken with the ruler, the measuring of the distance wo from A, wo from B, wo from C, and wo from D, wo from E and F, etc. gives me the same distance. The distance will not differ at any corner of the point taken on the circle and measured with the distance from the fixed point in the center. So we have many mathematical properties which arise through the circle. We have many mathematical properties which come into existence through this investigation outcome. So what are the different things we see here? For a perfect circle, the first point is that center wo must be fixed. Center wo must be fixed. And secondly, the center must be at equal distances from any point on the circle. The second point is that center wo must be at equal distances from any point on the circle. So this is how we define the perfect circle. For a perfect circle, the center O must be fixed. The fixed pointer of the compass must be fixed at that point when you draw the complete circle. You cannot move it in midway. Is how I understand the center O must always be fixed. Secondly, the center O must be at equal distances from any point on the circle. So when I take a ruler and measure the distance OA, OB, OC, OD, OE and OF, etc., all the distances must be same. Even if one distance is not the same as other distances, then the circle is not perfect. It is not a circle. Mathematically, a circle has two basic properties: center fixed and center at equal distances from the points on the circle. It's how we understand the circle derived from these two basic properties. The mathematical definition of a circle. Now that we have defined circle in the mathematical sense, now comes what are the key factors involved in a circle. Like every solid figure every figure which we have been discussing exclusively, like triangle, a parallelogram or other objects which are discussed in the previous session, had their own basic understanding of the structures through the sides, angles, vertices, areas, etc. Similarly, a circle is also examined for similar kind of properties in understanding the structure of a circle. Key factors involved with the circle. Key factors involved in the circle. So what are the key factors involved in the circle? So let's take a circle and understand the key factors. More importantly, identifying the key factors in a circle. So here is the circle which is obtained through the pointer of the compass. So this pointer makes me understand that this is the center of the circle. So the fixed point from where the circle is derived is called center of the circle. So here comes center of the circle. So this point is called the center of the circle. Next comes the fixed distance. Now the second property we have identified in the mathematical definition is that this point is at equal distances from any point on the circle. So what is that equal distance called? The center is denoted by O or C, or generally I denote the center with C and my point on the end to be denoted by some P. So P is a point such that here the distance from center to one of the points of the circle is P. So what is CP called? Initially, the fixed point denoted by C is called center of circle. The fixed point C is called center of circle, and the distance from center to any point, that is the fixed distance, CP, is called radius of circle. So this is given by the special name called radius of the circle, as it defines the radius, the curvature. Therefore, the distance CP is called radius of the circle. So circle has two important key factors. One is the center, one is the radius. The fixed point being the center of circle and the fixed distance being radius of circle. Radius and center for the circle with fixed distance and derived circle is how we understand the key factors involved with a circle. Now that we have discussed about the center and the radius, now comes the question on how we can connect the center and radius, or how we can define the radius in different ways of understanding radius. So here the session is about understanding the radius. So radius, as we see, is the fixed distance from the center to any point on the circle. That is, when I take a circle and when I take the center, this distance is called radius. CP, the distance CP is called radius, but sometimes radius is also represented by the line segment CP. So radius is generally denoted by small r. So when I represent the radius, I represent with r is how we define the radius. So radius denoted by r. And it's very important to note that radius is represented in both ways. Sometimes it is represented with line segment CP, which is r, and sometimes it is represented by length CP, which is r. So the two ways of representing radius, one is through the line segment CP, which is r, and one is through the length, which is mod CP, which is equal to r. But both mean the same, and radius is generally denoted by r. Is how we understand the radius connected with understanding the radius. And the most important understanding is, say for example, I take a circle and a circle. So what is the difference I identified between each of the circles? How do we identify these three circles? Clearly, I see that the radius of each of the circles is different. How different? What is the relation between radius of this and this and this? So let me take the radius of the first circle is r1, the radius of the second circle is r2, and the radius of the third circle is r3. Then how do I connect the radius of r1, r2 and r3 is the biggest question out here. Clearly I can see that this is r1, which is smaller than r2. So I see here r1, which is smaller than the next radius, which is r2, and this is more smaller than r3. That is, the highest radius is this and the smallest radius is this. This is how it comes in ascending order. So the radius of the first circle R1 is less than radius of the second circle, which is R2, less than radius of the third circle, which is R3. Therefore, I clearly understand that as the value of the radius increases, as the length of the radius increases, the circle becomes bigger and bigger. So finally, we conclude that the radius of the circle decides the size of the circle. Very simple. The radius being small, the size of the circle is small. The radius of the circle being bigger, the size of the circle is also very big. Is how we understand the radius connected with the circle. Here I have a disk. The radius of this bigger circle is bigger, and the radius of this circle is smaller than the radius of the previous circle, and the radius of this circle is smaller than the radius of the outer circle. The radius of the smaller circle is the smallest, the radius of the bigger circle is the biggest. Is how we connect this with understanding the radius of three circles. So my learning outcome here is the radius of the circle decides the size of that circle. So here my learning outcome comes out to be that the radius of the circle decides the size of that circle. Smaller the radius, smaller the circle. Bigger the radius, bigger the circle. The size of a sun or the size of an earth, which are circular in shape, or the size of a moon, are decided by their radii, by the radius of the earth, the moon, the sun, etc. Radii is plural form of radius. Is how we connect the radius with the circle. Understanding the radius of the circle through its size. Now that we have discussed about the key factors involved with the circle, now comes the understanding of a circle in a planar region. Today's session is about a circle in a plane. So let's see how a circle divides the plane into different regions. Circle in a plane. So a circle in a plane. So let's take this plane of the marker board. So on this whiteboard, I have a circle in this planar region. So in this planar region of the white marker board, a circle, it divides it into two regions. This is the region inside and this is the region outside. So a planar region with a circle makes it with two regions. One is which is called interior region because it is inside the circle, and this which is called exterior region because it is outside the circle. So for a circle divides the plane into two regions. One is interior and one is exterior. So I come to the conclusion. A circle divides the plane into two regions. A circle divides the plane into two regions. One is interior region and the other is exterior region. Interior and exterior region. The region inside the circle refers to the interior region. And the region outside the circle refers to the exterior region. Is how we understand the interior region and the exterior region in the circle. A circle divides the plane into two regions. Interior region denoted by this and exterior region as referred in the entire plane of the marker board. It's how we understand the regions inside the circle and outside the circle connected with a circle. Now that we have defined the interior and exterior region when a circle divides the plane into two regions, let's understand what a circular region is defined in the branch of mathematics. Circular region and its definition. So what is a circular region? Let's recap with the interior and exterior regions as discussed in the previous session. Now I have a circle on this white marker board. Then I have understood the region inside, which is interior region, and the region outside, which is exterior region, are the two regions out here. Now, here is the circle as denoted by the round rim. So what is the circular region in this? So here, the circular region is defined in mathematics to be all the interior region, which is denoted by this, including the circle. So circular region in mathematics is defined to be the interior region including the circle, but all the exterior region is not taken into account. So circular region is interior region plus circle is how we understand the circular region connected with the circle. Circular region equals interior region as represented by the dotted plot and the circle, but not the exterior region. This equals interior region plus circle. It's how we understand the contrast between interior region, exterior region, and the circular region. Now that we have discussed about circle and its various properties, most importantly, how a perfect circle can be constructed on a plane. The regions, the different regions which define a circle, the interior region, exterior region, and the circular region. Now comes the discussion of further properties of a circle. Today's session is about chord of a circle. So let's see what chord of a circle is in today's session. Chord. What is a chord? So let's see the definition in brief for a chord of a circle. For this, let's draw a circle. Imagine I have a circle in which I would like to define a chord. So here, the chord is defined for a circle to be the line segment which joins any 2 points in a circle. So here I have a circle for which I take 2 line segments. I have to take 2 points which make the line segment on the circle. For example, I take a point here on the circle and I take another point out here on the circle. Now, this point on the circle is denoted by A and this point on the circle is denoted by B. So for these 2 points A and B on the circle, a chord is defined as the line segment joining any 2 points. In this case, joining the points A and B. So let's join the points A and B for this circle. So here I have a line segment which joins any 2 points on the AB. So this line is called the chord. Is how we define a chord. A chord is defined as the line segment which is formed by joining any 2 points on the circle. Is how we define a chord. A chord is a line which cuts the circle. Is how I understand geometrically. The definition out here in words is that a chord is a line segment which joins any 2 points on the circle. So a chord is a line segment which joins any 2 points on the circle. In this case, the 2 points A and B are joined to form a line for the circle, and this line AB is called the chord. So in this diagram, line segment AB is the chord. Is how I understand the definition of the chord. A chord is a line segment which joins any 2 points on the circle. In this case, AB being the chord. Is how I understand a chord connected with the circle. Now that we have defined a chord, let's see in the session continued how many possible chords can I draw for a circle. With the definition of the chord is followed by the number of chords investigated for a circle. So this session is about chord with possible number of chords for a circle. Is what we're going to see in the session. So now that we are defining about, we are investigating the possible number of chords for a circle, let's take a circle and investigate with joining of 2 points, because a chord is defined itself when we join any 2 points of the circle. The line segment which is obtained by joining any 2 points in the circle is a chord, is the definition itself which we are going to investigate with various points taken on the circle. So let's take a circle and various points on the circle. So here is the circle which defines. Now for this chord, for this circle, let me take 2 points out here. So I denote this point with A1 and I denote this point with B1. So this chord is obtained when I join the points A1 and B1 on the circle. So A1 is a point on the circle and B1 is a point on the circle which is joined. So the line segment A1, B1 defines a chord. Defines one of the chord. Now let's take possible number of other set of points. I take a point and then join with other point on the circle and say this point is referred on the circle with A2 and this point on the circle is referred with B2. So I have another line which is formed, the line segment which is formed when I join the points A2 on the circle with B2 on the circle. So this is one more line segment. Therefore, by going with the definition of the chord, I can say proudly that A2, B2 also is a chord because this line is obtained when I join 2 points on the circle. A line segment which is obtained when joining 2 points on the circle is a chord, and hence A2, B2 is a chord. Is also a chord. Let's investigate with one more set of points taken on the circle. So let me take a different set of, here I take a point and here I take a point, and then I join the 2 points. So I take these two and I join so that I get this point on the circle is denoted by A3 and say this point on the circle is denoted by B3. Now clearly this also forms a chord because this line segment is obtained by joining the 2 points on the circle and hence by definition is a chord. Therefore A3, B3 is also a chord. So by this time of investigation, what do we conclude? We conclude that we have different sets of chords formed by different points on the circle. Therefore, as we have infinitely many points on the circle, therefore the infinitely many points equally join to form infinite number of chords. Since a circle has infinite number of points, there will be infinite number of pairs of points which can be joined to form infinitely many line segments and hence infinitely many chords. Here's how we understand the number of chords in the circle. So we have here, since a circle has infinitely many points, therefore infinitely many line segments are possible. Many line segments are possible, joining the pair of points for each infinite points, each pair joined with each other. Therefore, since a circle has infinitely many points, therefore infinitely many line segments are possible in the circle. Therefore, that is, a circle has infinitely many chords. So we conclude that since infinitely many line segments are possible through infinitely many pair of points on the circle, therefore all those lines by definition of chord, form the chords for the circle. Therefore, a circle has infinitely many chords. Chords is how I understand a circle and its chord. A circle has infinitely countless number of chords is how I understand through the session's investigation. Now that we have discussed about a chord of a circle, now comes the most important concept used in circles connected with chords. Diameter is what we're going to discuss in today's session. Diameter of a circle. So what is a diameter? Now that we have discussed about a chord being defined as a line segment which joins any 2 points on the circle, similarly a diameter has its own definition. So let's see how a diameter is defined and how we connect the chord with the diameter. To start with, the definition of the diameter. So in order that I define a diameter for a circle, let me take a circle into consideration. So here is the circle out here. Now this circle has the center. As we know that every circle is derived from the fixed point which is the center. So this circle also has the center. Say my center out here is this dot. Now let me just take the definition before I understand the diameter. So here comes the definition of the diameter. A diameter of a circle is the line segment which passes through the center of the circle. Now here we have many line segments which pass through the circle, but there's only one fixed line which passes through the center. So here any line which passes through the center is called diameter. Suppose I have a line AB which passes through the center, then I call this line AB as diameter. AB is the diameter. So in this diagram, since AB passes through the center of the circle, since AB passes through the center of the circle, therefore AB is the diameter, is how we conclude the diameter of the circle. So in this diagram, this is the diameter. Diameter of a circle is AB and its definition is given out here. So we finally conclude that a diameter of a circle is the line segment which passes through the center of the circle. So here this is the diameter because this passes through the center. If I take a line AB which does not pass through the center, then this line is not a diameter, but this line is a diameter because it passes through the center of the circle. Is how we understand diameter of a circle connected with a circle. Now that we have defined a diameter connected with the circle, now comes the concept of how we connect a diameter with the chord. How do we understand diameter through the chord definition as we have taken in the previous session? So this session is about connecting diameter with the chord of the circle. Diameter versus chord. So in order that we understand diameter in terms of the chord, let's revisit the chord definition. So chord is defined. A chord is defined as the line segment which joins any 2 points of the circle. Is how we understood the chord. That is, when I take this in terms of understanding through the diagram, I have this to be a chord Suppose I take the points A and B. This is a chord. Is how we understand. The line joining any 2 points of the circle is a chord. Then what is diameter and how is it connected to the chord is clearly understood through this definition, because when we say diameter, diameter is a line which passes through center of circle. So if I connect any 2 points in such a manner that it passes through center, then I can say that a line segment or a chord which passes through the center is the diameter, because a chord is nothing but defined even for a diameter. So if I take the line segment P and Q passing through the center, then clearly I can say that PQ is a special chord for the circle and PQ is given by the name diameter, because any line which passes through the center of the circle is a diameter, and hence the special chord PQ passing through the center must be the diameter for the circle. So here I understand that AB is the chord but cannot be the diameter, because this line AB does not pass through center, but the line PQ is the diameter. Is the diameter because it passes through the center. Simply, since it passes through center is how we understand the chord connected with diameter, or a diameter connected with the chord. And importantly, we have to understand that if I take the length of this chord and the length of this chord, we clearly understand that the diameter, which is also a chord, will be the maximum length. So length of the diameter will be maximum. it is the highest chord in the circle, also is one way I can connect with. So here I make the learning outcome that diameter, which is nothing but a chord, is the longest chord in the circle. So AB, PQ are the chords in which PQ is the longest chord because it is a diameter passing through the center. So my learning outcome here is that diameter is the longest chord in the circle, is how we understand the relation between a diameter and a chord. Diameter derived from a chord passing through center of circle. Now that we have related chord and the diameter for the circle, where diameter is nothing but a chord derived with a special case of passing through center. Now comes the discussion of how many possible diameters we can draw for the circle. Today's session is about the possible number of diameters which can exist in a circle, investigating the number of diameters in a circle. Possible number of diameters in a circle. So let's see with a circle taken into consideration and investigate on the possible number of diameters in the circle. I have a circle Now let's say the center of this circle is here. Now as we know that diameter is a chord passing through center of circle, therefore let's take the different possible chords which pass through the center from various different directions of the circle. So if I start from this direction, I have a chord A1, B1 with a point A1 out here and a point B1 out here in the circle. Similarly, let me take another chord passing through the center in some other direction. So here I have A2 and B2. So here I have a point A2 which is taken on the circle and the point B2 taken on the circle in such a manner that all these three are collinear. Let me take one more in some other direction. I take here so here I have another line passing through this center. So this is A3 and B3. So here is different set of lines taken into consideration, but interestingly all three lines are passing through the center of the circle. That means all the three lines as drawn here, the dotted lines, are the diameters for the circle by definition of diameter. Therefore initially I take A1, B1 which is a chord, a special chord, and hence is the diameter. Similarly, I take another line A2, B2 out here. which is a diameter. And similarly, I have the third one, which is A3, B3. So as I see here, since there are infinitely many points on the circle, I have infinitely many pairs of lines which I can make passing through center. So therefore, for infinitely many points in the circle, I have infinitely many diameters coming into existence. So my learning outcome here is that for any circle I take into consideration, the possible number of diameters in the circle are infinitely many. So therefore, there are infinitely many diameters in the circle. So coming to this, I can just draw the conclusion that since a circle has infinitely many points, since a circle has infinitely many points, therefore there exists infinitely many lines passing through the center of circle. Therefore, I conclude that since there are infinitely many lines which pass through center of circle, therefore a circle has infinitely many diameters. So this is the conclusion we make in case of number of diameters. My learning outcome, a circle has infinitely many diameters, is what we come into investigation of diameter. Now that we have defined a diameter and the possible number of diameters which can be drawn for the circle, let's see by taking into consideration two different diameters and see if the lengths are equal. This session is about investigating the lengths of the diameters for the given circle. Lengths of diameters. So let's see the lengths of diameters for the circle. Let me take a circle and let me consider two specific diameters for this circle. Now since I have the circle with center out here, let me draw two diameters passing through the center. Is what we get out here. So here I have a diameter AB which is passing through the center of circle, and I have another diameter CD also passing through the center. So there are two diameters AB and CD are the diameters for the given circle. Now as we take a ruler and measure the length of AB and then measure the length of CD, interestingly we come to the conclusion that they are same. Let's take another possible diameter, which is in different angle, which is EF, and measure this diameter also with the ruler, we see that all the three lengths are equal. So here I see that by observation my AB length will be equal to my CD length, which is equal to EF length, which shows that any diameter taken with a circle will have the same length. Therefore, my learning outcome here is that all diameters for the given circle must be of equal length. Therefore, the conclusion: all the diameters for the given circle will have equal length, is how we understand the conclusion for the given diameters. So all the diameters for the given circle will have equal length. That's how we conclude for the diameters connected with the lengths. Length of AB equal to length of CD equal to length of EF. Now that we have discussed about length of diameter, let's also investigate for length of chord. What would be the length of chord? Will all the chords have same lengths? Just like all diameters for the circle have equal lengths. Let's investigate the same property for chord lengths. So length of chord. So let's take a circle and investigate the different sets of chords to see if all the lengths are equal. So let me take a circle. Now here, let me take two different set of chords or three different set of chords for the same circle. As we know that a chord is the line segment which joins any 2 points of the circle. So let me take a chord which joins these two line segments, which is A and B. Next, let me take another chord which connects this with this. Is how we understand. Let me take one more chord which joins these two lines. Of this, I find this chord to be very small. AB is the chord, CD is the chord, EF is the chord. And clearly I see that the length of CD is the highest, the length of EF is the smallest, and the next smallest is AB. So as we see these three chords for the circle, what strikes our mind is that all chords will not have equal length. Clearly, because if I take the points very near to the circle, then obviously the line segment joining them will have a smaller length. If I take 2 points very far away on the circle, then the line joining those 2 points will be a bigger length. So I make the learning outcome that with the chords, clearly chords AB, CD and EF for the given circle are not of equal lengths, as the reason being that the pair of points which we consider will decide the length of the chord. So ABC and this for the given circle are not of equal lengths. Therefore, I conclude all chords of the circle are not of equal lengths, is how I conclude for the circle. All chords of the circle are not of equal length. And also it's very important that the length of the chord is decided by the pair of points chosen on the circle. This pair chosen gives me a smaller length of the chord, and this pair chosen gives me the bigger length of the chord. So my learning outcome also is the length of the chord is decided by the respective points chosen for that circle. So here I have a learning outcome which is very important. Step. All chords of the circle are not of equal lengths. Also, the length of the chord is decided by the respective points chosen for that circle. These respective points chosen gives me the smallest length of the chord for the circle out here. These set of points chosen for the circle gives me the longest or the bigger length of the chord. And the highest chord is a chord which passes through the center of the circle, which is the diameter. So here the diameter will be the highest chord or the longest chord. So any chord which passes through center will be the longest chord and its length being the maximum. And therefore, we have also seen that the diameter is the longest chord in the circle. The diameter is the longest chord in the circle, is how we just come to the conclusion. The diameter is the longest chord in the circle. Length of chords of the circle are not of equal lengths, is how I conclude the session. Now that we have defined the various properties in a circle, most importantly the chord and the diameter, now comes how we connect the diameter with the basic definition of circle. I'm talking about the radius of the circle. So how do we connect the radius with the diameter? Is the biggest question in the session. So let's see this session about connecting the diameter with the radius of the circle. So let's see how the radius and diameter are connected for the circle. So in order for understanding these two combined together, let's take the circle into consideration. So here is a circle. Now for this circle, clearly I know that the radius is the line joining the fixed center to any point on the circle. So here I have this distance to be the radius. C is the center, say my P is out here. So clearly I know that the line joining the fixed point to any point in the circle, that is CP, is the radius. And then let me extend this line to cut the circle on the other side. So here this line extends to cut the circle on the other side, say at Q. So this point is Q and this point is P. Now here I clearly understand that now CP is the radius and CQ also is the radius, because the other side of the circle, if I see, the line joining the center to any point in the circle is also the radius. So CP and CQ are the radii for the given circle. This part being the radius and this part being the radius. This also is the radius. Now, diameter. How did we define diameter in the previous session? A diameter is a chord which passes through center of circle. Now clearly when I see the line PQ, this seems to be a chord which passes through the center. Therefore, these two radius combine to form the diameter. Therefore, if I see the combined, PQ is the chord passing through center. Therefore, PQ is the diameter according to definition of the diameter. So the whole of PQ forms a diameter, as can be seen here. Also, it is very important to note that my PQ, which is taken out here, PQ is nothing but PC plus CQ. Because when this and this is joined, I get the bigger line. So PC plus CQ is PQ. So let me denote this radius with small r, and then my CQ and CP are equal. Therefore, this being r implies this also will be r. So my CQ also is r. And let me denote my diameter with d. So d is my diameter, r is my radius, which are equal, these two being of equal length. Therefore, each of them is r. So my PQ, which is d, is substituted for d in place of PQ. And then my PC or CP is clearly the radius, which is r. And again, my CQ, which is radius r, is substituted for CQ again for r, which on further simplification gives me d equals r plus r, which is 2r. So I find that there's a relation which connects the radius with the diameter, that is d equals 2r. That implies, how do you understand the statement d equals to 2r? D being the diameter and r being the radius connected with d equal to 2r implies the diameter of the circle is equal to twice the radius of the circle. So here I understand that diameter of the circle is twice the radius of the circle. Is how we understand the diameter connected with radius. Diameter is always 2r. That is, diameter of the circle is twice the radius of the circle. Two radius combine to form a diameter. Radius plus radius equal to diameter. D equals 2r. Diameter versus radius. Now that we have connected diameter with the radius, with diameter being equal to twice the radius of the circle, now comes the concept on understanding the arc of the circle. Today's session is about arc of a circle. So let's see the definition of arc of a circle. So let's consider a circle to understand its arc. So here is the circle with center out here. So what is an arc? As we see that the rim of the circle is this, so any part or piece of that rim which we find in the circle is called an arc. So as an arc is defined for a circle to be a part or piece of a circle, is how we understand arc. So for this circle, my arc is defined as the part or piece of a circle is called an arc. Is how we define an arc. So how do we define the part or piece of a circle? So imagine I take this part of the circle. So this part of the circle, let me darken up out here. So I have here a part of the circle which is arc. So if I take any 2 points in the circle, then that curved part of the circle between the endpoints is called an arc. Mathematically, an arc is defined to be the part or piece of a circle is defined as an arc. So there can be any 2 points taken on the circumference of the circle and we get any number of arcs. So arc connected with the circle. So in this case, AB is the arc. Note that for an arc, I use the symbol curve because a line segment AB is denoted by AB, which is called the line segment, and a curve deriving from A and B for the circle is denoted by AB, which is called an arc. So the symbol what I put on the top defines for this to be an arc and this to be a line segment. An arc always has a symbol this on its top. So AB is the arc for the circle as given here. The part or piece of a circle is called an arc. Is how we understand the arc. An example in real life is a pizza. When you take a pizza and cut the slice, we get the pizza with its space, and the outer part of the pizza defines an arc. A piece of pizza connected with an arc. So outer face with endpoints taken as P and Q defines an arc. So PQ is an arc. with its symbol is how we understand arc of a circle. A part or piece of a circle is an arc. Since there are different number of arcs, now that we have defined an arc to be a part or piece of a circle, let's see the possible number of arcs for a circle. This session is about investigating the possible number of arcs for a circle. So let's take a circle to investigate the possible number of arcs. Imagine I have a circle out here with its center. Now let me take a pizza cut in different shapes. Say I cut this out here, and I cut a bigger piece out here, and I cut totally 1, 2, 3, 4. So I have totally 4 pieces which are cut for the pizza. So I have the piece number 1, which is out here. And piece number 2, which is out here. And piece number 3, and then the piece number 4. So totally I have pizza number 1, 2, 3 and 4 pieces. So let's investigate each of the piece. So the first piece which I cut, let me take the endpoints AB, and for the second to be CD, and the third to be EF, and the fourth to be GH. Now each of the endpoints are taken for the pieces, with the first piece with endpoints AB, second piece with endpoints CD, and third piece with endpoints EF, and the fourth piece with endpoints GH. So I have totally 4 pieces of the pizza. So in this case, I see the length of this arc on the outer face is AB, CD, EF, and then here the length of arc is GH. So each of the arcs have different lengths, this being AB, CD, EF and GH. So there are different possible lengths of arcs which can be identified in a circle. If I cut the pizza into 100 times, I get different number of pieces with different lengths of arcs. So my outcome here is that conclusion, there are infinitely many lengths of arcs for the given circle. There are infinitely many lengths of arcs for the given circle. Different arcs for different lengths of pizzas, different pieces of pizzas, is how we investigate that depending on the size of the pizza piece, the length arc changes. Bigger the pizza piece, bigger is its length of arc. Smaller the pizza piece, smaller is its length of arc. Is how we understand the length of arc and the possible number of arcs for a circle, with the conclusion that there are infinitely many lengths of arcs for the given circle. and all arcs are not of same length, they are of different sizes. So the lengths of arcs can be of different lengths, is how we conclude through the arc and the circle. Now that we have defined the arc and the possible number of arcs in a circle, we have come to the conclusion in the previous case of different pieces of the pizza that as the size of the pizza differs, the length of its arc differs. Therefore, we connect the previous concept with the session, which is major arc and minor arc. This session is about major and minor arcs for a circle. Minor and major arcs. So let's see the definition in brief. So let me take a circle in order to understand the two basic definitions for a circle. So let's see how we can understand the minor and major arc. Imagine I take this pizza and cut it into two pieces, such a way that I take the knife and cut it from the center of the pizza, slicing towards this. And I cut this, slicing towards this. Then when I remove this pizza out, I get two different sets of pizzas in this manner. So I get a pizza which is this, and I get another set of pizza which is so here I have two pieces of pizza which are obtained when I slice it in the center. Now as I see these two slices of pizza, what is that I observe is the biggest question out here. So clearly I see that this pizza has a very big length of the arc. This is also an arc, but these two arcs have a wide difference. That is, this is bigger in size and this is smaller in size. Therefore, any arc which is bigger in size is called major arc, and the arc which is smaller in size is called minor arc. So here comes which is called minor arc, and this which is called major arc, because this is bigger in size and this is smaller in size. So let's try to make the conclusion which says the arcs which make out the bigger and smaller. The longer arc of the circle is called major arc. And the smaller arc of the circle is called minor arc. So this is how we define the two basic arcs in the circle: the major arc and the minor arc. The longer arc of the circle is called major arc. The smaller arc of the circle is called minor arc. Is how we understand the relation between two arcs of the circle and major and minor arc. Major arc, the longer arc of the circle; minor arc, the smaller arc of the circle. Now that we have defined the major arc and the minor arc for the circle, now comes the discussion of a special case called the diameter. If I have a diameter for the circle, how do we try to take into consideration the arc connected with the diameter is what we're going to investigate in today's session. This session is about investigating the arc for the diameter of the circle. Diameter versus arc. In order that we understand the arc connected with the diameter of the circle, let's take a circle connected with the diameter. As we all know that a circle with the diameter just simply has a line passing through the center of the circle. I have a circle with the diameter. Suppose I have the diameter out here. Is how we connect. Now this circle assumed as a pizza, I would like to cut the pizza along the diameter. So I just try to cut the pizza in this diameter direction. So clearly I get two slices of the pizza. So here I get slice 1 and slice 2. So here is the first slice and here is the second slice. Now with these two slices of the pizza, I have the center which is common in this case. So what do we observe from the arc as obtained here and the arc which is obtained in the other piece of the pizza? So clearly I see that for this pizza, cut into two pieces, arc 1 is the arc obtained for the first pizza and arc 2 is the arc obtained for the second pizza, and clearly they are equal because this line exactly cuts the pizza into two equal pieces and therefore we get two equal length of arcs, which makes us conclude that when we take the diameter into consideration, the lengths of arcs obtained by the diameter of the circle are always equal. That is, when I take the diameter, this arc length must be equal to this arc length, is how we conclude. So, the arc lengths, the arcs obtained by the diameter of the circle, the arcs obtained by the diameter of the circle are always of equal lengths. So this is one of the investigation concluded that if the arcs obtained by the diameter of the circle are always of equal lengths. is how I conclude the conclusion. Diameter makes the two arcs to be equal. So here arc 1 equals arc 2. Is how we conclude for two pieces of pizza. This defines two equal pizzas. Arc length of this pizza equal to arc length of this pizza. And also it's very important to note that this semicircle, when divided along the diameter, forms two semicircles. So this circle, when divided, forms semicircle 1 and semicircle 2. Is how we conclude the diameter connected with the arc. Now that we have discussed a special case of the diameter and the circle with its arc, a diameter defines equal lengths of arcs for a given circle, is what we have concluded. Now comes the discussion of semicircle. Let's see how a semicircle is defined through the diameter for the circle. Semicircle versus the circle. So the word semi itself says exactly half of the previous circle. So semi is half of the circle. Therefore, if I take a circle then half of it is a semicircle. So clearly, when I pass through the diameter, the center lies out here. If I cut the circle along the diameter, I get a semicircle, is how I understand the semicircle. So here, this is a circle and this is a semicircle. For the circle and the semicircle, let's see the lengths of arcs, how the arcs are defined. So for this, I have two arcs which are formed along the diameter. This is arc 1 and this is arc 2, which are of equal lengths. So let me say the length of this arc is L. Then because the first arc is equal to the second arc in the diameter passing through the circle, therefore the length of arc being L also makes this to be L. And as we have seen, a semicircle is nothing but exactly half of the circle, so this length must be equal to this length. So clearly we see that each of the arc lengths are equal. Therefore, a semicircle is now defined in terms of the arc length. So let's see how we can define a semicircle for the given circle through its arc length. A semicircle is a part or piece of the circle whose arc length is exactly half of the circumference of that given circle is how we understand a semicircle. A semicircle is a part or piece of the circle whose arc length is exactly half of the circumference of the given circle. So if the circumference of this circle is, say, L or 2L, then the arc length of this semicircle will be L, because half of the total 2L is L. So given the circumference of the circle, a semicircle will have its arc length exactly half of the circumference of the circle, is how we understand the arc length connected with the semicircle for the given circle. Semicircle versus circle versus arc length. Now that we have defined the arc length for the circle, now comes the question of what would be the highest arc length of the circle as a special case. Today's session is about circumference of the circle connected with arc length. Circumference of a circle. So let's see what circumference is. Let's take a circle with certain center and certain radius. So here I have a circle, and for this circle I have the part or piece of the circle which is defined as an arc. So what if I don't cut the circle? A circle itself is said to be a part or piece of itself. So a circle itself is called a part or piece of itself. Therefore, the whole circle itself defines the arc, is how we understand in the general sense. So here we define the circumference to be the length of the complete circle is called circumference. So my circumference is defined as the length of the complete circle is called circumference of the circle, is how we define the circumference of the circle. So in this case, this whole of the length is called the circumference. Is how we define circumference of a circle. And interestingly, we see that for every arc length which are of different sizes, a circumference is the highest arc length for the given circle, or the longest arc length for the given circle. So my learning outcome here is that the circumference is the longest arc length for the given circle, or the maximum arc length for the given circle. Is how I understand the circumference connected with arc length for the given circle. The longest arc length for the circle is defined as the circumference for the complete circle. Now that we have discussed about circumference and arc lengths connected with circumference as a special case, now comes the new concept called segment. So let's see how geometrically a segment is defined for the given circle. This session is about segment of a circle. Segment of a circle. In order that we define segment of a circle, let's take a circle of suitable radius and center. Now, as we take the chord into the session, we know that a chord is a line segment joining any 2 points of the circle. So let me take the 2 line segments which join the chord to make the chord. So AB is the chord for the circle. Now clearly I see that when I make the chord in the circle, I always have 2 regions made by the circle. So when I just draw the chord for the circle, I have 2 regions made within the circle. This is how we get the different regions. So there are 2 regions made by the chord AB. So chord AB makes 2 regions within the circle. So this is region 1 and this is region 2. So these regions are called segments. The regions made by the chord within the circle are called segments. So now we define a segment to be the segments are the regions made by the chord within the circle. So segments are the regions made by the chord within the circle. So here the upper part is 1 segment and the lower part is 1 segment. So I have 2 segments for this. One is this and the other is this. So this is 1 segment which is defined for the circle, and this is one more segment as defined out here, with AB being the endpoints of the chord. So region 1 and region 2 are the 2 segments for the given circle. Segment are the regions made by the chord in the circle, and there are always 2 segments in the circle. Because a chord divides into 2 regions, there exist always 2 regions which are the segments for the circle. Now that we have defined segment of a circle to be the region as made by the chord within the circle, now clearly we have come across the conclusion that there are 2 regions formed by the chord of the circle. So here let's see in today's session about possible number of segments made by the chord in the circle. So possible number of segments for a circle. So today's session is about the possible number of segments for a circle. So let's take a circle for understanding the number of segments. So here is a circle, and let's take the chord. I have a chord AB out here, then clearly I see that this chord is making two regions, region 1 as denoted by dotted lines, dotted dots, and this is region 2 as given by slanting lines. So region 1 and region 2 are the two regions formed by this chord AB. So any chord of the circle always makes two regions, region 1 and region 2. Therefore, I conclude that for any chord of the circle which makes two regions within the circle, therefore, there always exist two segments for the circle. Is how we define the segment connected with number of segments. Since every chord makes two regions, within the circle, therefore every chord makes two segments. Therefore, possible number of segments for a circle is equal to 2. The number is 2. Therefore, number of segments made by the chord with the circle is equal to number 2. Is how I understand number of chords made by the chord, number of segments made by the chord with the circle is equal to number 2. Two segments for the circle, for any circle given in the branch of mathematics. Now that we have defined the segment and also explored the possible number of segments for the circle, now comes the question on what are those two segments called with specific names, and how do we define each of the segment or each of the region is what we're going to see in the session. Today's session is about major segment and minor segment. So let's see the basic definitions of major and minor segments. So let's classify the given circle into two different cases. Major segment and minor segment. As we all know that a segment is a region obtained when a chord intercepts the circle. So therefore, every circle makes two regions with the chord. Let's see which region would be called the major segment and which region would be called minor segment with its own specific definitions. So imagine I take a circle with the chord AB. then clearly I find two regions in this chord. This is region 1, segment 1 and segment 2. But geometrically, I identify that there is only one segment which has the center of the circle, but this does not have the center. So this has the center of the circle and this does not have the center of the circle. And this is how, with the property through which we classify the segments into major segments and minor segments. So let's first take the segment which has the center of the circle. So in this case, my first circle which has the center of the circle, and my second case of the segment which does not have the center of the circle. And then the segment which has center involved, the center of the circle involved, is called major segment, and the segment which does not have the center of the circle involved is called minor segment. So for this circle, this part is called minor segment and this part is called major segment because it has the center. So major segment is a segment which involves has center of circle in it, and here does not have center of circle in it, is how we understand the major segment and minor segment involved with the circle. The segment of the circle which has the center of the circle involved is called major segment, and the segment of the circle which does not have center of circle involved is called minor segment. Is how we define major and minor segments for the given circle. Now that we have discussed about major segment and minor segment, now let's connect the arcs, the major arcs and the minor arcs related with the major segment and the minor segment. This session is about connecting major and minor segments with their respective arcs. Major and minor segment connected with arcs. So let's see how the major and minor segments are connected with their respective arcs. For example, let's take a circle of suitable radius and center. So here I take a circle with the center out here. And here is the chord AB. Now I have the regions denoted with this. Now in this case, I have two regions, the first region and the second region. Now clearly we know that the region 1 has center, so this is called major segment. As discussed in the previous session, that major segment is the segment or the part of the circle which has center involved. Now because it has the center involved in this region, this dotted region is called major segment. Now this part of the circle does not involve the center, or there's no center of the circle in this region. So this is called minor segment. Is how we understand the major and minor segment. Now comes the question on how we connect them with the arcs. So let's revisit the definition of arc of a circle. We know that major arc is the arc which is bigger in size, and minor arc is the arc which is smaller in size. So obviously this acts as the minor arc, and this acts as the major arc. So what do we conclude from these two connections of the segments and arcs is that the length of the arc of the major segment or the major region is major arc, and the length of the arc of the minor segment or the minor region is called minor arc. Is how we understand the major and minor arcs connected with major segment and minor segment. So here the arc connected with major segment is called major arc, and the arc connected with minor segment is called minor arc. Is how we understand the relation between major arc and minor arc. The arc connected with major segment, that is the bigger segment, is major arc, and the arc connected with smaller segment, that is the minor segment, is minor arc. Connecting major and minor segments with major and minor arcs. Now that we have defined the segments and the arcs and the diameter and the radii, all the different connected properties of a circle, now let's see the new property or the concept called sector of a circle. Sector is today's session for the topics of circle. What is a sector? Let's define sector using the circle with suitable radius and center. So let's take a circle of suitable radius and this. Imagine this as a pizza, and I would like to define a sector through the real life model of a pizza. So let's consider a pizza which is cut exactly through the center. Say I cut this slice. So this is the piece of the pizza which I cut out there. And thus I obtain a piece of pizza out here. So this is the piece of the pizza through which I define a sector. Before that, let me take into consideration that this piece of pizza, as taken from the main circular pizza, has the center of the circle, has radius has arc length. So a sector is a region which is enclosed between the two radii and the arc length. So a sector is now defined a sector is the region enclosed by the radii and the connected arc length. So this is said to be the connected arc length between A and B and O. So connected arc length between the two radii is between OA and OB, that is AB is the connected arc length. So sector is defined to be the region enclosed by the radii and the connected length of circle and the connected arc length is how we define the sector for the given circle. A pizza cut with a piece of pizza has the center, has the radii, has the arc length, and a sector is the region enclosed by the radii of circle and the connected arc length is how we understand a sector in terms of the arc length. Sector with its definition. Is how we define a sector of a circle, part of a circle, a piece of a pizza for a given Domino's pizza. Now that we have defined a sector, now comes the question on what are the different types of sectors which exist for a given circle. This session is about the types of sectors of the given circle. The types of sectors for a given circle. Just like we had the different definitions for an arc, we had major arc and minor arc. Even for segments, we had the classification of segments into two types, major segment and minor segment. Similarly, we classify sectors into two forms, of course, major sector and minor sector. So let's see the definitions in brief. So the sectors are classified into two types. One is major sector and the other is minor sector. So how do we define major and minor sectors is the biggest question out here. So in order for that, let's take the circle into existence. So let's take a circle out here with the center fixed and with suitable radius. Let me cut this pizza assumed to be a circle into a piece. So I cut the piece of pizza out here, and one of the slice is this and the other slice is this. So I have two slices of the pizza. One is this and the other is this. So what is the difference between these two slices is what defines the two types of sectors. Now as we know that the circle defines two sectors, one is this and the other one is this. So there are two types of sectors identified here. One is this and the other is this. So here let me take the two possible sectors with the first piece of pizza which is taken out here, is out here, and the second set of pizza which is taken in this case, which is like this, out here. Obviously this slice of the pizza is bigger in size and this slice of the pizza is smaller in size. Therefore we call this as major sector and this as minor sector. Mathematically, a major sector is a sector which involves major arc. So this sector has major arc and this sector has minor arc. So therefore, a sector which has major arc involved is called major sector. A sector which has minor arc involved is called minor sector. Major sector is a sector which involves major arc for the given circle. Minor sector is the sector which involves minor arc for the circle, and hence the smaller piece of the pizza is called minor sector and the major piece of the pizza is called major sector. Is how we define the two types of sectors classified in the branch of circles: major sector and minor sector. Now that we have defined the sectors into consideration and the different types of segments taken into consideration, let's take the special case of the segments, the maximum possible segment or two equal segments taken in a circle. Connecting the segment through the diameter is what we are going to discuss in the session. Segment through the diameter is the session about. Through the diameter. Let's take this as a special case where the segment is through the diameter. We have defined a segment to be a part of the circle when the chord is taken into consideration. That is, when I take a circle and the chord, the two regions are called the segments of the circle. Now let's take the possibility of what if the chord passes through center? What if the diameter is taken into consideration? So let's take a circle in defining a segment through the diameter as a special case. So here I have a circle where I have the center out here. So imagine my chord here is the diameter itself. So this diameter also forms two regions out here. The region 1 and region 2. So I have two regions, region 1 and region 2, formed by the diameter. And interestingly, we also note that the two regions as formed by the diameter AB are equal because they are exactly through the center. Area of region 1 is equal to area of region 2 because AB is the diameter. It exactly divides the circle into two equal parts. Therefore, I conclude that so the two segments are equal. the segments as made by the diameter of a circle are equal in area. Therefore, the segments as made by the diameter of the circle are equal in area. That is, area of the region 1 is equal to area of region 2. Is how we understand the segments when connected with the diameter AB. The segments as made by the diameter of a circle are equal in area, and hence the major segment and minor segments are equal. And also, when I take each of the segments, I get a semicircle. Is how I understand each of them being a semicircle. So when segments are divided along the diameter, they form two different semicircles, and therefore also the two segments as formed are called semicircles for the given circle, because this is the other way of defining a semicircle through the segment definition. The segments as made by the diameter of a circle are equal in area. Also, the two segments as formed, region 1 and region 2, are called semicircles for the given circle. This region is called the semicircle 1 and this region 2 is called semicircle 2. The two segments, when formed through the diameter of the circle, will form two semicircles, is what I make as the learning outcome. Semicircle connected with segments through the diameter as a special case. Now let's see some additional chord properties in a circle. So today's session is about the chord and the angle subtended by the chord at a point. It can be the center of the circle or at any circumference of the circle. So today's session, angle subtended by a chord at a point. So let's see what exactly we can understand through angle subtended by the chord before we understand the properties connected. What do we mean by angle subtended by the chord? So let's take a circle to understand the concept more better through the geometrical means. Suppose I take a circle and I take a chord. So for this circle, my chord is AB. In this case, we understand the angle subtended by the chord to be, say for example, by the chord at a point. Angle subtended by the chord at a point implies, if I take a circle with the chord AB out here, then let me take a point P on the circle. Now let's see what is the angle subtended by this chord with respect to the point P for the given circle. Angle subtended by the chord at a point P. So let's understand the concept through this circle diagram. So as we have the chord AB out here and the point P, I understand that this chord makes an angle with point P. We understand the endpoints of A and B for the chord make some angle with the point P. To some extent, let's see how it makes an angle with the point P. The left end of the chord AB joins with P, and the right point of the chord AB also joins point P in a manner that it subtends an angle, and this is called the subtended angle made by the chord AB. So here this angle is called angle subtended by the chord AB out here. AB, and this angle is being subtended converging up to the point P. So this refers to the angle subtended by the chord AB with respect to the point P. Chord AB at point P is how we understand angle subtended by the chord AB. If I take, say, for one more chord LM, so here is the chord LM, and here let me say there's a point Q. Then angle subtended by the chord LM with respect to the point P is similarly understood as the endpoint, the first endpoint L connected with the point, and the second endpoint M connected with the point, and then this refers to the angle subtended by the chord LM at point Q. This is the angle subtended by the chord AB at point P, and this is the angle subtended by the chord LM at point Q. Is how we understand the angle subtended by the chord with respect to the point. It's also very important to note that, say for example, I have a circle in which I have a chord AB. Say I have a point P out here. So let's see if the angle which I make on this diagram is the angle subtended by the chord AB at P. So let me just join this, and let me just join this. Now let's see the difference between the angle as made by the chord AB with P and the angle made by certain distance in the line AB with point P. I clearly see that this angle is not subtended till the end of the right end of the point on the chord, but it is exactly just before the line or the chord AB. So clearly I understand that the rule for angle subtended by the chord with the point is that both the end points of the chord must subtend an angle such that we get a subtended angle of the chord. But since this gets subtended with the point, this does not get subtended with the point, therefore I say this is not the angle subtended. This is not the angle subtended by chord AB This is not the angle subtended by chord AB at point P, because this region is left over, since this region is left over, is how I understand the angle subtended by the chord at point, any point. It can be on the circle or other way. Angle subtended by the chord at a point for the given circle. Now that we have understood the definition of angle subtended by the chord at a point through the geometrical understanding of the circle, let's see some extended properties connected with angle subtension. So the first property which connects the chord and the angle subtended by the chord is as follows. So here my session is angle subtended by equal chords at a point. So let's see how the equal chords subtend an angle. So the property here says that two chords, here is the property statement, two chords which are equal in length subtend equal angles at the center of its circle. This is how the property comes. So the first property, which connects angle subtended by equal chords at a point, states that two chords which are equal in length subtend equal angles at the center of its circle. So let's see this through the geometrical circle diagram. Imagine I take a circle. Now the property says that if I take two chords which are equal in length, so let me take chord AB and CD which are equal in length. So I take the chord AB and I take the chord CD, provided they are equal in length. So with the first condition that the chords are equal in length, I have chosen the chord AB and the chord CD which are equal in length. That is, AB equals CD is the first condition which I take into existence. Chord AB equals chord CD. Now the property says that when I take the case of two equal chords, then the angle subtended by each of the chords will also be equal at its center. So suppose I have my center out here, then the angle subtended at the center by chord AB, and say this angle is some θ1, and the angle subtended by chord CD, say this is the chord CD, and the angle subtended at its center O is θ2. Then clearly the property says that for equal chords which are equal in length, the angle subtended at its center must be equal. Therefore, implies for equal chords AB equal to chord CD implies the angles subtended at its center being θ1 and θ2 must be equal, is how we understand the property. Two chords of equal length subtend equal angles at its center of the given circle, is how the property holds for any circle and any equal chords taken into consideration. Property number 1, connecting angles subtended by equal chords at a point are equal, is how we come with the property. Now that we have seen the angle subtended by a chord at a point, let's see the relation between the length of the chord and its respective angle subtended at the circle, center, or any of its circumference. This session is about finding the relation between length of the chord and angle subtended. Relation between subtended angle and length of chord and its length of chord. So let's see how we can relate the subtended angle and its length of chord. So let's take a circle and understand the concept through the investigation of the length of the chord and its subtended angle. So here is the circle, and here, say for example, I take a chord AB, and here I have the center. Let me take another chord CD. Then clearly there are two subtended angles made by chord AB and chord CD. Say the chord AB subtends an angle at the center of the circle. This being the center, subtends an angle, say theta 1. There's another chord CD which is bigger in length, as clearly we can see that chord AB is smaller than chord CD and chord CD is bigger than chord AB. Therefore, the angle subtended by this chord CD with the center of the circle at the center, this. So we see that this angle is theta 2. So angle subtended by the chord AB at the center of the circle is theta 1, and the angle subtended by the chord CD at the center of the circle is theta 2. So we have two angles. Let's see the relation between the two angles. So here, since length of chord AB is smaller than the length of chord CD. Therefore, I clearly see that this makes a smaller angle and this makes a bigger angle, smaller than the length of chord CD. Therefore, chord AB makes smaller or subtends smaller angle at center O of the circle, and chord CD being bigger, chord CD subtends a larger angle at center O, is how we understand bigger the chord or bigger the length of the chord, the bigger is the angle subtended at its center. So here we come with the conclusion that the size of the angle subtended by the chord at its center of circle depends on the length of the chord. Is how I conclude the size of the angle subtended by the chord at its center of circle depends on the length of the chord. Bigger the length of the chord, bigger is the angle subtended at its center. Smaller the chord, smaller is the angle subtended at its center. So clearly I have here theta 1 is smaller than theta 2 because chord AB is smaller than chord CD. Longer the chord, longer is the angle. Smaller the chord, smaller is the angle, is how I conclude the session. Now that we have seen a property connecting angles subtended by equal chords at a point, subtended by equal chords at a point, we have seen that if two chords are of equal length, then they subtend equal angles at the center of the circle. Now what would be the converse? Will the converse hold true for the same property? If I say that the two chords subtend an equal angle at the center, will the chords be of equal length? Is the reverse way of understanding the converse of the property which we have seen. So let's see the converse of the previous property, connecting angles subtended by equal chords at a point. So here my question in the converse is, will the chords which subtend equal angles at the center, equal angles at the center of the circle be of equal lengths? Is the question which we are going to investigate through the converse. So here I have the investigative question which says, will the chords which subtend equal angles at the center of the circle be of equal lengths? The answer is yes. Two chords which subtend equal angles at the center of the circle must be of equal length. We can just try with geometrical ruler and the compass through which we can investigate the property. If I take a circle, if I take two chords which subtend equal angles at the center of the circle, center of circle being O, I have the chord AB and the chord CD which subtend equal angles. Now since they subtend equal angles, it is assumed in circle property that the side opposite to those angles must be equal. So because these two are equally subtended angles at the center of the circle O, therefore by converse the two chords must be equal. That is, since chords AB and CD out here subtend equal angles at the center O of the circle, therefore the two chords must be of equal lengths, is how I understand the property. The two chords must be of equal length, provided they subtend equal angles at the center of the circle. So proudly I can say converse holds true. That's how we understand converse holds true for angle subtended by equal chords at a point. Now that we have discussed about the chord properties connecting angles subtended by the chord at its center or at its circumference of the circle given. Now let's see some additional properties connecting the chords. This session is about the property number 2 of the chord properties connected with the circle. So this property 2 mainly refers to the perpendicular line connecting with the chord, or how they are geometrically connected to each other. So let's see how a perpendicular line drawn through a center of the circle to the chord makes some new interesting geometrical properties coming into existence out here. So here the property says that the perpendicular here is the property number 2, which says that perpendicular distance, the perpendicular from the center of the circle to the chord bisects the chord, is how we understand the property. The property says the perpendicular from the center of the circle up to the chord bisects the chord. So this is one interesting property which is identified in investigating a chord through its perpendicular distance, which is passing through circle. So let's see how it bisects the chord. So here I take a circle, I take a chord. So here AB is my chord connected with endpoints A and B on the circle. Now let's take the center of the circle. Here is the center of the circle. Now the property says the perpendicular from the center of the circle to the chord bisects the chord. So from center of circle, I drop a perpendicular. So here I have a perpendicular, say CD, out here. So this perpendicular CD bisects the chord AB. That is exactly, it passes through the midpoint. So when I understand this, when I drop a perpendicular from the center of circle to the chord AB, the foot of the perpendicular exactly lands at the middle point between equal distances. So here we have the property which says the perpendicular, when dropped from center of circle to the chord, exactly lands in the middle, that is, exactly bisects the chord AB. Is how we understand. C is center of circle, CD is perpendicular, from center of circle C to chord AB. So CD is perpendicular distance from center of circle C to chord AB, and D is foot of perpendicular. So here I have center of circle, perpendicular distance from center to the chord AB, and D is foot of perpendicular. So the property says AD must be equal to DB, or CD bisects AB, is how we understand the learning outcome connecting the perpendicular from center of circle to the chord AB. They are equal, or CD bisects AB. This is always true when a line passing through center is perpendicular to the chord AB. Bisecting property of a chord. Now that we have seen the property connecting the perpendicular line which bisects the chord, let's see if the converse of the same property holds. Today's session is about the converse of the perpendicular property. So let's investigate the converse. So my converse question comes out to be will the perpendicular line or will the line passing through center of circle and bisecting the chord be perpendicular to that chord is my question out here. So the question here is, will the line passing through center of circle and bisecting the chord be perpendicular to that chord? So this is what is the center of attraction in the converse. So let's see if it makes perpendicular. This is the converse of the previous statement. Perpendicular line passing through center bisects the chord. But what if a chord passing through center and bisecting the chord, will it make the line to be perpendicular to the chord? Is what is the investigation in the converse. So let's see if this holds true. Here is a circle. Now I have the center of the circle. Let me take a chord AB. So here is chord AB and here is the center of the circle. And the line passing through the center of the circle is in such a manner that if I take a line passing through the center of the circle, then such a way that it bisects the chord here. So here it cuts at D. This cuts at D. Now here, let me take the line L which passes through center. So here L is the line passing through center C L is the line passing through center C of the circle and bisecting the chord AB, that is exactly cutting the chord at midpoint D. Therefore, AD equals DB, or D is midpoint of AB. Here is the chord AB. Now, the converse says that this line must be perpendicular to the chord. So, the answer to my question is yes. If a line passes through center of circle and bisects the chord AB, then the line must be perpendicular to the chord AB. Is how we understand the converse. Therefore, that implies CD or line L is perpendicular to line AB, or we can also say CD is perpendicular to AB, is how we understand the property connecting the line and the chord. Line is perpendicular to the chord is how we understand the properties connecting the circle. So converse holds. Is how we understand the converse holds true for the property connecting the perpendicular line with the chord passing through the center of circle. Now that we have discussed the chord properties connecting the circle, now comes the concept of connecting a chord and a point, connecting a circle and a point. So this session is about investigating the number of circles which can be drawn through a point, or 2 points, or 3 points taken into consideration. Initially, to start with, number of circles which can be drawn through a unique point or 1 point. So today's session, chord, circle connecting the points. Circles passing through a point. So let's investigate, or before that we try to understand what do we mean by circle passing through a point. So let's see the circles passing through only one unique point. For example, I take a point P. So here I have a point P through which I would like to draw the circles. So for example, I have a circle which passes through point P. I can equally have another circle which passes through the same point P. I can also have another point, another circle which can pass through the same point. So like this, I see there are infinitely many circles which I can draw through those points. So what does this give? An indication. So here is circle 1, circle 2, circle 3 and circle 4 passing through the point P. So this gives me a clear idea that there are infinitely many circles which can be made to pass through one fixed point. So in this case, we understand that circles C1, C2, C3 and C4 pass through the same point P. So my learning outcome in this case is that infinitely many circles, of course of different sizes, not of the same size, many circles pass through a fixed point in the plane. So here my fixed point being P. So in this case, my fixed point is P, is how we understand. So my learning outcome here is infinitely many circles pass through a fixed point in the plane. Is how I understand infinitely many circles passing through only one fixed point, point P. Now that we have discussed about the number of circles which are possible to be drawn passing through a fixed point P, what happens if I take more than one point, that is 2 points on the plane? So my investigation in this session is about investigating the number of circles which are made to pass or which can be made to pass through 2 points in the plane. So this session connected with circles passing through 2 fixed points in a plane. Circles passing through 2 fixed points in a plane. So here let's investigate by taking 2 fixed points in the plane. Suppose I take 2 fixed points out here. So let's see how we can draw the different circles through this plane. Now with these 2 points, I have a circle which is made to pass through. So here I have a circle which passes through these 2 points. Similarly, I have another circle which passes through these 2 points. Next, let me take, yes, this is one more circle which is made to pass. And next, we have this. So here I find that for 2 points, say P and Q, which are fixed in the plane, there are infinitely many circles which can be drawn through those fixed points. Taken with, this is circle 1, this is circle 2, circle 3, circle 4, etc. So like this we can draw with different curvature or radius of curvature the different sets of sizes of circles but passing through the fixed points P and Q. So here P, Q are fixed points in the plane, and C1, C2, C3, C4, etc. are the circles through P and Q. So what do we make the learning outcome here? Just like in the previous case, I make the learning outcome that there are infinitely many circles which can be drawn passing through the fixed points P and Q in the plane. So here my learning outcome infinitely many circles can be drawn passing through two fixed points in the plane is how I make the learning outcome. Two infinitely many circles can be drawn passing through two fixed points in the plane. The same property for one fixed point in the plane or for two fixed points in the plane, there are infinitely many circles which can be drawn through them. Now let's try to extend our investigation through 3 points taken in the plane. How many circles can I draw if I have 3 fixed points in the plane? Is what is the investigation connected with number of circles and the fixed points in the plane. So this session is about circles passing through three points. So let's see for 3 points taken into consideration. So here we clearly have a property in the statement which says that there is one and only one circle which passes through the given three non-collinear in the plane. So here the property is restricted to a finite number. That is, there is only one circle which can pass through the given 3 non-collinear points in the plane. The condition is for non-collinear points taken in the plane. That is, if I have three non-collinear points in the plane which are fixed, then the theorem says that there is only one circle which can pass through these 3 non-collinear points. Is how we understand the property. A, B, C are non-collinear points where only one circle can be drawn. I cannot draw any other circle which can pass through all the 3 points. It is impossible to draw any other second circle passing through these 3 non-collinear points. Therefore, for the points A, B, C are non-collinear points. So here A, B, C are non-collinear points and only one circle can be possibly drawn passing through A, B and C. Is how I understand the circle connecting 3 points. For 1 point, infinitely many circles can be drawn passing through that 1 point. For 2 points, infinitely many circles can be drawn passing through those 2 points. But for 3 points taken in the plane A, B and C, which are non-collinear, there's only one circle which can be drawn passing through A, B and C. So my statement says there is one and only one circle which passes through the given 3 non-collinear points in the plane. Circles connecting 3 points. Now that we have seen the property connecting 3 points, that there is only one and only one circle which can pass through 3 non-collinear points. Now the question is, what if the points are collinear? So today's investigation is about finding the possible number of circles which can pass through the 3 collinear points. Three collinear points. So let's see, if I take 3 collinear points, how many circles can be drawn passing through all 3 points. Say my 3 points are A, B and C, which are in the straight line. Collinearity in the sense they are in the straight line. So I have the points A, B and C which are collinear. If I see that any circle I draw either through these 2 points does not pass through the third point, any circle passing through these 2 does not pass through this, and hence I have 0, or I cannot draw any circle passing through all the 3 collinear points. As the best I can draw is this, or the best I can draw is this. I clearly understand that for collinear points A, B, C, no circle can be drawn passing through all 3 points A, B, C. It is impossible to draw a circle passing through all 3 points. So my learning outcome in this case is it is impossible to draw a circle passing through all 3 collinear points. Passing through all 3 collinear points is how I make the learning outcome. It is impossible to draw a circle passing through all 3 collinear points. If the points A, B, C are collinear, there are no circles which can be drawn passing through all those 3 collinear points. For non-collinear points, there's only one circle which can be drawn passing through all 3 points. For collinear points, 0 circles. For 1 point, infinitely many circles. For 2 points, infinitely many circles. Is how we conclude the different possible cases taken into consideration. 3 collinear points taken in this case, with no circle can be drawn. Now that we have discussed about circle passing through 3 points, we have come with an interesting outcome that there's only one circle possible to be drawn through three non-collinear points. Now let's see the three non-collinear points and the circle through which we give a special case of a circumcircle. Today's session is about circumcircle, connecting with three non-collinear points in the plane. What is circumcircle? So let's see how circumcircle is defined. Let me take a triangle ABC and connect the circle properties with that triangle. So initially I take a triangle ABC. Suppose I take three non-collinear points . Say the three non-collinear points are A, B and C. So for these 3 points, we have already discussed that there's only one circle which can be drawn passing through these 3 points, non-collinear points A, B, C. So A, B, C are non-collinear points in a plane. So let me just join the points and see what kind of a figure we get. So here we get 3 points A, B and C. And these 3 non-collinear points, when I join, forms a triangle ABC. ABC is a triangle when each of its vertices are joined. And we know that ABC are the vertices of the triangle. So for any 3 non-collinear points in a plane, when we join, we get a triangle through 3 vertices A, B and C. So let's see how we define a circumcircle for this triangle. So by going through the 3-point theorem, we have only one circle which can be drawn passing through all this. Is how we get a triangle with only one circle passing through A, passing through B and passing through C. So we have a circle passing through exactly the vertices of the triangle. So any circle which passes through all the 3 vertices of a triangle is called a circumcircle. Circumcircle definition. A circle which passes through all the vertices of a triangle. For example, for this triangle ABC, this circle passes through the vertex A, vertex B and vertex C. So a circle which passes through all the vertices of a triangle is called a circumcircle. Is how I understand a circumcircle connected with triangle ABC. Here is the triangle ABC and here is the circle passing through the vertices A, B and C, and this is called circumcircle. connecting the triangle with the circle properties. Circumcircle connected with triangle. Now that we have discussed about circumcircle being a circle which passes through all the three vertices of the triangle, now comes the understanding of circumcenter. Circumcenter is the topic of the session. What is a circumcenter? So here we have a center, that means we are talking about the center of the circle. So clearly the circumcircle is very much connected with the circumcenter. So let's take the circle and understand the circumcenter for that particular circle. So let's take a triangle initially. So here I have a triangle A, B and C, and here I have a circle which passes through all the three vertices of the triangle. So here I have vertex A, vertex B and vertex C. Therefore, since this circle passes through all the three vertices A, B and C for the triangle, this is no doubt for being a circumcircle. Now clearly we identify the center of this circle as somewhere in this region of the triangle. So the center of this circle, which is clearly in the triangle at some region, is called the circumcenter, because this center of the circumcircle is connected with the triangle at this point. So circumcenter is identified to be the center of the circumcircle. So here this point is called circumcenter. Is how we understand the circumcenter for a given circle. So definition of circumcenter. The center of the circumcircle, the center of the circumcircle is called circumcenter. Is how we understand the circumcenter O out here is called the circumcenter for this circumcircle. So here point O is circumcenter. Center of the circumcircle is called circumcenter. Is how we understand the concept. Now that we have defined circumcenter, now comes the understanding of circumradius for a circumcircle. This session is about circumradius for a given circumcircle. So let's discuss about circumradius. Circumradius. What is circumradius? Let's take a circumcircle to understand the concept circumradius. So let's take initially a triangle ABC, for which I had to draw a circumcircle. So here I have a triangle ABC and then I have a circle which clearly passes through all the 3 points. in this manner is how the circle passes through all 3 points. And clearly we know that such a circle which passes through all the 3 vertices of the triangle is what we define as circumcircle. Now that we have defined circumcenter to be the center of this circle, say it lies somewhere here, then clearly I see that the distance of this center from the vertex A and from vertex B and from vertex C is same, because this is the center of the circle. The distance of the center from each of the vertices is same. That is, I have OA equals OB equals OC, because it is same radii, since same radii, and hence this equals this equals this, and that radius of the given circle is called circumradius. For circumradius is defined to be the radius of the circumcircle is defined as circumradius. So let's come with the definition. The radius of the circumcircle is defined as circumradius. Therefore, we define the radius of the circumcircle is defined as circumradius. Is how we define for a circle. The center of the circle, the center of the circumcircle is called circumcenter, and the radius of the circumcircle is called circumradius. And when we talk about the circumcircle, it's a circle which passes through all the 3 vertices of a triangle ABC. Is how we understand circumcircle, circumcenter, and circumradius. Now that we have discussed about various properties of circle connected with chords and radius and center and triangles, etc. Now comes connecting the circle with perpendicular lengths. So initially, let's try to understand what do we mean by the perpendicular length or the perpendicular distance. This session is about understanding length of the perpendicular. Length of the perpendicular. So let's see how we understand length of the perpendicular through the geometrical means of understanding. Imagine I take a line L. Here is a line L, and then I have a point P out here. So now I would like to define the perpendicular length from P to line L. So if I drop a perpendicular from a point P up to the line L, I clearly understand that this gets dropped straight out here, exactly perpendicular. Say it drops at M. So here the length PM is called length of the perpendicular. So this length which we define from point P to the line L is called length of the perpendicular. So here I have clearly the perpendicular distance, which defines as length of the perpendicular from point P to the line L is nothing but the distance PM, which we refer. So this is how we define the length of the perpendicular. Length of the perpendicular from the point to the line L is how we understand length of the perpendicular. It's very important to note also that the length of the perpendicular is the shortest length from the point to the line. If I take different set of lines, the perpendicular length is the shortest. Let's see in brief how this becomes the shortest. Now that we have defined the length of the perpendicular, now comes what is the special case, or what is the significance of the length of the perpendicular. How is it special as different from other lengths? Let's investigate the length of the perpendicular from a point to a line L. This session is about shortest distance from a point to a line. Shortest distance from a point to a line. I have a line and I have a point. Now, as we can see, one of the perpendicular length is this, as clearly drawn out here. And there are other lines also possible from point P to the line L. Like we have different lines which I can draw from point to the line. Now clearly I can see that if this is M and this is L, Q, S, etc., I find that all the lines from P to L are a bit far away, but the shortest is the one which is straight drop perpendicular. So out of PS, PM, PL and PQ, I find PM to be the shortest because it is the perpendicular length. So my learning outcome here is that if the line is perpendicular length, then that line, that distance or that length will be the shortest, is what we make the learning outcome. Now because this is dropped at perpendicular, this is perpendicular, and therefore this makes me understand this is the shortest. So this is the shortest. This is the shortest length of all, is how we understand the shortest length of all is PM. So my learning outcome in this case is that the perpendicular length or the length of the perpendicular is the shortest length from a point P to a line L is how I make the learning outcome. Is how we make the learning outcome. The perpendicular length is the shortest length from a point P to a line L. So in this case, from a point P to a line L, the shortest length is this. Is how we understand the shortest length connected with length of the perpendicular or the perpendicular length. PM is the shortest length in this case. Now that we have discussed about length of perpendicular and various other properties of circle, now let's see a property which connects the chords and their distance from the center. Distance of the chords from the center is how we understand the distances. So this is about connecting the chord properties with their distances from the center. Chord properties. So let's see the property which says that if I take two equal chords in a circle, then the property says that those equal chords will exactly be at equal distances from the center. So let's make a statement and understand the concept geometrically through a circle and equal chords. So here I have a statement: equal chords of a circle are equidistant from the center. Equal chords of a circle are equidistant from the center of that circle. Is how the statement comes out. How do we understand this statement geometrically? The statement says equal chords of a circle are equidistant from the center of that circle. So here the condition is equal chords will be equidistant from center of that circle. So let's see geometrically to understand this concept. So here I have a circle. Here is my circle and I have two equal chords. Say, here is my chord and here is my other chord, and both the chords are of equal length. So AB is the chord and CD is the chord for this circle in such a manner that they are equal. AB and CD are chords such that they are equal chords. So this equals this is how we understand the equal chords. Now we have to show that they are equidistant. So clearly the property says that if this is the center of the circle, then the distance from this point to the line is perpendicular length. So here comes the perpendicular length from the center to M N. So here I have OM and ON which are equidistant. So the property says that for this circle which has equal chords AB and CD, they are equidistant from the center. That is, the distance of O to AB, which is OM, will also be equal to the distance of O from CD, which is N, and they are equal, is what the property says. They are equidistant from the center. So here OM equals ON. That is, they are equidistant from the circle. Is how we understand the property. So in this case, AB, distance of center O from chord AB is equal to distance of center O from chord CD, is how we understand the property. The distance of the center from chord AB is equal to distance of center O from chord CD, simply because the two chords are equal. AB equals CD. If the chords are not equal, then they won't be of equal distances. This property holds only when the chords are equal. Now that we have discussed the property, let's try to investigate the converse. The converse of the chord property as discussed in the previous session. So let's see the converse statement. So here we have the converse holding true. That is, the statement for the converse says, if the chords are equidistant from the center of the circle, then the chords will be of equal length. This is how we understand the property. If the chords are equidistant from the center of the circle, then the chords will be of equal length. They must be of equal length. This is how we understand the converse. Let's see geometrically the property. This is the circle, this is the center, and I have two chords. AB and CD. Now these two chords are exactly at equal distances from the center O. The two chords are equidistant from the center of circle, then the converse says the chords must be of equal length. Now these are equidistant, therefore the chords must be equal. So here I take OM equals ON. O is center of circle and AB and CD are chords of the circle. And it is given that they are equidistant, so OM equals ON. Since they are equidistant from the center, then The converse says under these three conditions implies the two chords must be of equal length. The length of the chord AB must be equal to the length of the chord CD. So I write this in this way, that length of the chord AB is equal to length of the chord CD. So is how we understand the converse. If the chords are equidistant from the center of the circle, then the chords must be of equal length. AB equals CD in this case. Converse holds true for chords. Now that we have discussed about various chord properties in a circle, now let's discuss about angle subtended by an arc. So we have this property which we need to understand through various properties connecting angle subtended by an arc of a circle. Let's see what is meant by angle subtended by an arc of a circle. Let's take the session. Today's session is about angle subtended by an arc of a circle. Angle subtended by an arc of a circle. Let's take a circle to understand the angle subtended by its arc. So here I have a circle, and then I have a center. So for example, the arc from A to B is how I take. So I take the part of the circle that is an arc from A to B, and I want to know this arc AB of the circle, what angle it makes with the center. So angle subtended by an arc of a circle is understood to be the angle made by the arc with respect to the center of the circle. For example, here is the arc AB. Now this is the angle as made by the arc with the center of the circle. Is how we understand the angle subtended by this arc AB with its center is this. So this angle is referred to as the angle subtended by an arc of the circle. So here this is angle subtended by the arc AB. So here when I take the center O and I take the arc, then the angle at which the end points of the arc converge is what is called angle subtended. So here is the end point which connects, and here is the other end point which connects, and hence we get an angle. So theta is the angle subtended by the arc AB at the center of the circle. Angle subtended. So here I have the definition. Angle subtended by an arc of a circle. Let's see the definition. The angle made by the arc, the angle made by the arc with its center is called angle subtended by the arc of the circle with its center is how is understood to be angle subtended by the arc of the circle at its center. It is not compulsory that the arc subtends the angle only at the center. Say for example, I take a point P and I would like to understand the angle subtended by this arc AB with respect to this point P. So I understand this as joining this, and here I get the angle subtended by the arc AB at point P. So whatever is the point, if the endpoints of the arc meet at that point, then the angle formed by the endpoints of the arc with that point is nothing but called the angle subtended by an arc of a circle with respect to that point. P is the point here and O is the point here. Here is the angle subtended at O by the arc AB, and here is the angle subtended by arc AB at P. So this angle refers to angle subtended by the arc AB at point P on the circle is how I understand the concept of angle subtended by an arc in the circle with respect to its point. Now let's try to investigate the connection between the chords and the arcs. So this session is about connecting the lengths of chords and lengths of arcs. So let's see how we can connect the chords and the arcs. Chords versus arcs. So here the property says that if I take two equal chords for a circle, then the two arcs will be of equal length, the arcs made by that chord. Let's see how the property holds. So here the property says that if I take a circle, if I take two equal chords, say AB is the chord and here CD is the chord, such that they are equal. Now clearly for these equal chords they make certain arc length out here. So this is the arc length as made by the chord AB, and this is the arc length as made by the chord CD. So the property says that the arc length as made by the chord AB will be equal to the arc length as made by the chord CD, simply because the two chords are equal. That means the circle property says that if two chords are equal, then they make equal lengths of the arcs. Chord AB is equal to chord CD, that implies arc AB is equal to arc CD, or they are congruent, is how we understand the property. Two chords of equal lengths make two equal arc lengths, is how we understand the property. In the statement, the property says two chords of equal lengths make two chords of equal lengths make the two arcs make the two respective arcs equal. In other words, they make them congruent, equal in all respects. So here the property says two chords of equal lengths AB equal to CD implies the two chords of equal lengths make the two arcs, the respective arcs, to be equal. So if chord AB equal to chord CD, then length of arc AB will be equal to length of arc CD. That's how we understand the property. Connecting chords with arcs. A chords connected with the arcs of the circle. Now that we have discussed a property connecting the chords and the arcs, if the lengths of chords are equal, then the respective arc lengths are equal. Let's see the converse. What if the arc lengths are equal? Will the chords formed by those arc lengths also be equal? Is the question out here. So let's see if the converse holds true. This session is about converse of the previous theorem. So let's see the converse. Statement. If two arc lengths are congruent, if two arcs are equal, more importantly, if they are congruent, then the respective chords formed by those two arcs will be of equal length, is how we understand the statement. If two arcs are equal, or they are congruent or equal in length, then the respective chords formed by joining the endpoints of the chords of the arcs to form a chord, respective chords formed by those two arcs will be of equal length. This shows that the converse holds true. That is, converse holds true. When I take geometrically, I understand that if I have a circle, if I have two arcs, say AB and CD, which are equal in length, AB which are equal in length, that is this arc equals this, then the chord as formed by AB and the chord as formed by CD must be equal, is what the property says. Arc AB equals arc CD implies the length of the chord AB must be equal to length of the chord CD. Converse holds true for the previous session. Given the statement, if two arcs are equal or congruent, then the respective chords formed by those two arcs will be of equal length. Converse holds true. Now that we have discussed about angles subtended by an arc of a circle, let's connect with what happens if the two arcs are equal. Will they subtend equal angle at the center? This session is about investigating angles subtended by equal arcs of the circle. Topic of the day: angles subtended by equal arcs of the circle. Angles subtended by equal arcs of the circle. So let's see how it comes. So here, let's take a circle. Say I have two arcs which are equal in length. Say for example, I have a circle where I have the arc AB and the arc CD. Now here, if I have this arc being equal to this, that is arc AB is equal to arc CD, then in that case the property says that two arcs which are equal in length subtend equal angle at the center. That is, if the angle subtended by the arc AB is this and the angle subtended by the arc CD is this, then the property says that this angle subtended by arc AB will be same as the angle subtended by the second arc CD. That implies angle AOB is equal to angle COD is what the property says. If the arcs are of equal lengths, their subtended angles will also be equal, is how I understand the property for angles subtended by equal arcs of the circle. Let's write the statement in words. So here the property says that two arcs of equal lengths subtend, or arcs of equal length subtend equal angles at the center of the circle, is how I understand the property connecting the arcs and the circle. So my learning outcome in this property states arcs of equal lengths subtend equal angles at the center of the circle. The arc AB equal to arc CD implies the angle AOB is equal to angle COD, is what the property states. Let's see the next property connecting the arc and the subtended angle. This is one of the most important property in the circle properties connected with arcs. We use this in many solve mathematical problems which are solved using the connected properties. This session is about connecting angle subtended by the arc at the center and at the circumference of the circle. So here comes arc properties. So here the property says, let's take a circle. And let me say AB is the arc. So here for the circle, AB is the arc. Now for this arc AB, the property says that angle subtended by this arc AB at the center, say this is the center, angle subtended at the center by this will be double the angle subtended by the same arc at any part of the circle. Say the arc subtends some angle at any part of the circle from here to here or down anyway. So let me pick a point P on the circle. So the angle subtended by this arc at P would obviously be when I join PA with PB. Is how I get. So here O is the center and this is called angle subtended at the point on the circle, which is this. So the property says that if the angle subtended at the circumference is theta, then this will be obviously double of that angle always, is what the property says. Any angle identified on the circumference is said to be connected with this in such a manner that if this is 30 degrees, this will be 60 degrees. If this is 40 degrees, this will be double of 40, which is 80, is how it goes on and on. So here the property says that implies angle AOB is twice of angle APB, is what the property says. Angle subtended at the center of the circle is double the angle subtended at any point on the circle. P is a point on the circle. So my statement says angle subtended by the arc at the center of the circle is double the angle subtended. The angles subtended by the arc at the center of the circle is double the angle subtended by it at any part of the circle. So here P is on any part of the circle. At any part of the circle is how we understand the double angle property of the circles. Angles subtended at center and on the circle are related through angle AOB is twice of angle APB, is how we understand the concept. Now that we have discussed one of the most important property in circles, angle subtended at the center of the circle is always twice that of angle subtended by the same arc at any point on the circle or any part of the circle. Let's see some other extended properties which are useful in solving many math problems connecting with geometry. This session is about connecting the angle property with the segments. So here angle property in a segment of a circle. Angle property in a segment of a circle. So let's see how the angle property is connected for the segment of a circle. We have already discussed that a segment is a line or a chord which divides the circle into two regions. Say, for example, I have a circle and I have this. Then clearly we know that AB is the chord which divides the circle into two regions, region 1 and region 2. Therefore, this is called major segment and minor segment. So here we have the segments as divided through a chord. So angle property in a segment of a circle says that if I take the chord AB and I take the subtended angle made by the chord AB. Suppose this is the angle as made by the chord AB with point P, and there's another point, say Q, and say the chord AB makes subtends an angle at the point Q. Say for example, this is the subtended angle for the chord AB at Q. Is what we get. So angle APB and AQB are said to be angles in the same segment. So APB and angle AQB are called the angles in same segment. So APB and AQB are called angles in same segment, is how we understand the two angles. So let's see how the property connects the angles in the same segment. The property says that angles which are always in the same segment are equal. So if this is theta, this will be equal to theta. So these two angles being angles in same segment implies angle APB is equal to angle AQB, is how we understand the angles in the same segment. APB and AQB are the angles in the same segment. So property connecting this. Angles in the same segment are always equal. Angle APB equal to angle AQB because they are angles in the same segment. Angles in the same segment are always equal, is how we connect the property. Now let's see the converse of the previous session. The property which says angles in the same segment are always equal. This session is about converse of the made statement. The converse of this session is very interesting because I can prove that I can draw a circle with the same segment property. That is, if I have a line AB this is the line AB, and say there are two more points P, or I take this to be C, and here is another point D, such that this line segment makes equal angles or subtends equal angles at this point. So the property says that If the chord AB subtends angle C with theta, then also if the chord AB subtends an angle, same angle at D, then the property says that if these two are the same subtended angles as made by the line segment AB with respect to C and D, then it is perfectly possible to draw a circle passing through all the 4 points. That is how I get a circle, is what the property says. If AB is the line segment and ACB angle is equal to angle ADB, that implies ABCD are concyclic. Concyclic in the sense they pass through the circle. All 4 points pass through the circle. That implies ABCD are concyclic. That is, they all pass through the circle, is how we understand the concyclic property of A, B, C and D. So here my converse property says that if a line segment AB subtends equal angles at C and D, in the plane, in this plane, then the points A, B, C, D are concyclic. That is, they all pass through the circle, is how we understand the property connecting the line segment which makes equally subtended angles and hence pass through the circle, connecting with concyclic with equal angle subtended, the converse of the segment theorem. This session is about cyclic quadrilateral. Now that we have seen many triangles where we can draw a circle passing through all 3 points, which is called circumcircle, we have already discussed about circumcircle, which is formed by joining all the 3 points of this triangle through a circle. So in such a case, now comes, just like the triangle where a circle is drawn connecting all 3 points, what about a quadrilateral? Can we draw a circle passing through all the 4 vertices of the quadrilateral, is what is the investigation. So investigating the quadrilateral versus circle. So let's see how we can relate a circle with a quadrilateral. For example, I take a quadrilateral A, B, C and D. Now, just like a triangle where we can draw a circle passing through all 3 points, it is not possible that every quadrilateral can be made to pass through the circle. There are only few quadrilaterals which have a circle formed exactly with all the four vertices. So we have a special case in which the difference comes that at least one circle, there is only one circle which passes through A, B and C is how we understand the triangle, and that circle is called circumcircle. But in case of quadrilateral, there may be a circle passing through A, B, C and D, but not always. Only few quadrilaterals have the circle exactly connecting or touching A, B, C and D. So this is one thing where we have a special case of a quadrilateral, that quadrilateral which is taken into consideration, which passes through all the four vertices, a circle which passes through all the four vertices. So let's take the special case of a quadrilateral, only that quadrilateral which exactly fits in the circle. This session is about cyclic quadrilateral. What is a cyclic quadrilateral? It is very simple with the definition itself, which says a quadrilateral which is cyclic or which forms an exact circle. So in most simple manner, we can define a cyclic quadrilateral to be a quadrilateral which can exactly fit in the circle, any circle of different radii. So for example, I take a quadrilateral which can exactly fit in out here. So the quadrilateral ABCD clearly fits in this circle, and hence this quadrilateral is called cyclic quadrilateral. Because it exactly fits in the circle. Since it exactly fits in the circle with center O is how we understand cyclic quadrilateral. So if I take this in the statement, quadrilateral a quadrilateral whose vertices pass through the circle is called a cyclic quadrilateral. That's how we understand a cyclic quadrilateral. A quadrilateral whose vertices pass through the circle. ABCD is a cyclic quadrilateral because all the four vertices A, B, C and D pass through a circle. Or in other words, this quadrilateral ABCD exactly fits in the circle, and hence such a quadrilateral is called a cyclic quadrilateral. Every quadrilateral is not cyclic, only few of them fit exactly in the circle. Is how we make the learning outcome cyclic quadrilateral. Now that we have discussed about cyclic quadrilateral, let's see some of the geometrical properties connected with those quadrilaterals which are cyclic. This session is about connecting the cyclic quadrilateral with its properties. Properties of cyclic quadrilateral. Let's see how we can do it. Properties of cyclic quadrilateral. Suppose I have a cyclic quadrilateral ABCD. So the quadrilateral ABCD is a cyclic quadrilateral. Then the property says that for a cyclic quadrilateral ABCD, the opposite angles always are supplementary. This and this are supplementary. So property says for a cyclic quadrilateral ABCD, angle A plus angle C is 180 degrees and angle B plus angle D, which are opposite angles, are always supplementary. So this plus this is 180 and this plus this is 180. So my other pair is how we understand the property. For a cyclic quadrilateral, sum of these two and sum of these two will always be 180 degrees. So we have the property which says opposite angles of a cyclic quadrilateral are supplementary. So opposite angles of cyclic quadrilateral are supplementary, that is 180 degrees. Is how we understand the supplementary and the complementary of the cyclic quadrilateral. Let's see the converse of the previous session. If the pair of opposite angles of a quadrilateral is equal to 180 degrees, then will the quadrilateral be cyclic? This session is about the converse of cyclic quadrilateral property. So the property says that if there exists a quadrilateral A, B, C and D such that the opposite angles A, B and D and A and C sum up to 180, that is, for a quadrilateral ABCD, angle A plus angle C equals 180 and angle B plus angle D equals 180 implies the property simply says that if the sum of opposite angles is 180 degrees, then the quadrilateral must be cyclic. All the four vertices must pass through the circle is how we understand the cyclic quadrilateral properties. That implies quadrilateral ABCD is cyclic, is how we understand the converse of the previous property. In general sense, my property says if the sum of opposite angles in a quadrilateral is 180 degrees, this and this being opposite angles, A and C are opposite, B and D are opposite angles of a quadrilateral. If the sum of opposite angles in a quadrilateral is 180 degrees, then the quadrilateral must be cyclic. There's no chance, there's no way, but the quadrilateral in that case must pass through all the four coordinates of the circle. Must pass through all the four coordinates for the cyclic property. Cyclic property holds true for the converse. Converse of cyclic quadrilateral property. Now that we have discussed about cyclic quadrilateral properties and including its converse, now comes the new property which connects internal angular bisectors of a quadrilateral. So let's see the quadrilateral which is formed by internal angular bisectors of the quadrilateral. This session is about internal angular bisectors of a quadrilateral. Quadrilateral and its internal angular bisectors. So let's see how this is connected with the cyclic quadrilateral. So let's take a quadrilateral to understand the concept more better. I have a quadrilateral ABCD. Say ABCD is a quadrilateral. Now for this quadrilateral, let me take each of the internal angular bisectors. Say for example at A, the internal angular bisector is this, and at B, the internal angular bisector is this, and at C, the internal angular bisector at B, and let's take an internal angular bisector at C. And an internal angular bisector at D. Say here I have a quadrilateral which is formed by each of the internal angular bisectors of A, B, C and D. So this quadrilateral which is formed by each of the internal angular bisectors, let me denote by P, Q, R and S. So the property says that such a quadrilateral which is formed by each of the internal bisectors, angular bisectors, will be cyclic. That means a quadrilateral which is formed out here which is PQ RS must be cyclic. It has to pass through a circle as what the property says. So this quadrilateral must be cyclic quadrilateral is what the property says. The quadrilateral which is formed by each of the internal angular bisectors of the actual quadrilateral will be cyclic is the property which connects quadrilateral and its internal angular bisectors. The property which says the quadrilateral which is formed by the internal angular bisectors of here it is PQRS which is formed by the internal angular bisectors of quadrilateral ABCD will be cyclic. So this quadrilateral which is formed by internal angular bisectors is cyclic. So this is the property cyclic quadrilateral connected with internal angular bisectors.